Okay, this video is going to give an overview of actually deriving the efficient frontier using Microsoft Excel. Now we know that the efficient frontier is the combination of optimal portfolios based on some feasible set of investments. So in this particular video, I'm going to assume my feasible set of investments that I'm using are the 7 stocks from my previous video. And I'm going to combine those together to look at the efficient set of portfolios that I can construct. Now, before we jump into this, we just need to quickly remember some theory regarding that efficient frontier. So we know that the efficient frontier are those particular stocks that, for a given level of risk, have the highest possible expected return, or alternatively, for a given expected return, have the lowest possible level of risk. And we know that the efficient frontier starts at the minimum variance portfolio. The minimum risk portfolio is always the beginning point because that is a unique portfolio. And because it has the minimum risk, it must be the best risk return trade-off for that point. The efficient frontier then moves in a curved manner, and it passes through a really important point known as the optimal risky portfolio. And the optimal risky portfolio theoretically is the combination of assets within our feasible set that maximizes the Sharpe ratio. Then it continues on beyond that optimal risky portfolio. And the other thing we know about the efficient frontier is we can take the optimal risky portfolio and we can combine that with the risk-free rate of interest, and we derive our capital allocation line. But there's some concepts that we'll come at in just a moment. So first of all, what I've got is here are the 7 stocks from my previous video: BHP, Foster's Group, and so forth. And in my previous video, what you'll remember is that I've actually calculated annualized standard deviation of returns and expected excess returns for each of those stocks. So watch the previous video for an overview of how I did that. But I've just pasted those values into the cell. So just the previously calculated values. For example, if we look at BHP, standard deviation of BHP 3.93 just comes from this cell here. And the expected excess return of BHP 0.062 just comes from this cell here. So I've got those calculated parameters based on my historical data, my historical standard deviation of returns, and my expected excess return, which is based on my beta coefficient that I've also calculated from the returns. Next of all, I've got my covariance matrix. Now my covariance matrix again is just the covariance matrix the variance covariance matrix I calculated earlier, where I just looked at the relationship between each of the stocks. So for example, this highlighted cell, I've got that the covariance between BHP and Foster's Group is 0.0243. Here in my variance covariance, the covariance between BHP and Foster's Group 0.0243. So those values are just from the previous data calculations as well. For now, I've just rounded all those to 4 decimal places, although probably ideally you would do no rounding and working out at all. Then, as discussed in my previous video, we can actually complete this matrix because we know that the bottom half of the matrix is just the mirror image of the top half. So for the cell I've got here, for example, the covariance between Westpac and Foster's Group is going to be equivalent to the covariance between Foster's Group and Westpac. So it's just the mirror image to get the full matrix there. Now what I've got along the side here in cells A18 to 24, these are the weights in each of these assets. So what I've got currently sitting here is an equal weighted portfolio where I've got 1/7 of my portfolio invested in each of these 7 stocks. And in cell A25, this is just a little check. It's the sum of all those portfolio weights. We know that the sum of the weights should always equal to 1. So I'm just making sure that's equal to 1. And those weights are replicated just along the top here. So that's just referring back to the equivalent weights. So what I can actually do is that as I change these weights, we'll find that these values down the bottom here change, because what they're doing is they're calculating the variance of my portfolio. Now what you'll remember is that the variance of a 7-asset portfolio is a matrix where we've got the sum of the weight of each of the assets times the variance of each of these assets plus 2 times weight times covariance for each pair of assets within that particular portfolio. So it's a long formula, as you might remember. It will have 42 covariance terms and 7 variance terms. Now we can calculate that if you actually add together all these cells here. If you go through each of the formulas, what I've done there is that in this cell at the bottom, A25, that is the weight of the first asset, BHP, times the sum product of these covariance terms and these weightings. Okay, so what that actually means is this cell here is weight of BHP times weight of BHP times variance of BHP, plus weight of BHP times weight of Foster's groups times covariance between BHP and Foster's group, plus weight of BHP times weight of Fairfax times covariance between BHP and Fairfax, and so forth. Okay, when I do the same in each of these cells, okay, the sum of all these values becomes the variance of the portfolio calculated using that long formula. Hence, what I've got over here in cell A28 is the standard deviation of that portfolio's returns. Given the sum of all these is the variance, okay, standard deviation we know is the square root of the variance, and square root is equivalent to raising to the power of 0.5. So the sum gives me the variance, and I take the square root to get the standard deviation. Next thing I've got here is I've got the mean excess return for this particular portfolio. Now we know that we calculate a mean expected return as the weights times the expected returns. Okay, these are calculated in excess returns at the moment, so therefore this will be a mean excess return. Some product just tells me add together each of the product of each pair in this series. So what this will do is it will say weight of the first stock times excess return of the first stock plus weight of the second stock times excess return of the second stock, and so forth all the way down, such that in cell A26 I've just got my standard expected return formula, and then in cell A27 I add back in that risk-free rate, add back in 0.05, and that just gives me my mean expected return. So I've got mean excess return and mean expected return. Now the reason I actually calculated mean excess return up here is because we know that the slope, which is actually our Sharpe ratio, the Sharpe ratio is calculated with excess return on the numerator and standard deviation on the denominator. So once I've got excess return in that cell, I can just calculate my Sharpe ratio as excess return divided by standard deviation of returns, and that's what I've got in this cell here. Just bringing that out. But if I reduce this down here, we can see that my slope is just 0.037 divided by 0.209, which gives me that Sharpe ratio there. So these values here are all my inputs. And what I'm going to do is I'm going to use those inputs to complete the table I've got on the screen here for my efficient frontier. So as I said earlier, 2 points I know with my efficient frontier. I know it starts at the minimum variance portfolio. It passes through the optimal risky portfolio, which is the portfolio where the Sharpe ratio is maximized. And then it will go through a series of points in between. So in order to calculate this, each of these points, what I'm actually going to have to do is I'm going to have to add in solver into Excel. So if I go add-ins, and I'm going to ask for the solver add-in to appear. Just like data analysis, that's going to appear under my data ribbon as a value called solver. So if I select solver, so what I'm going to do, and I'm going to say for myself here, for my minimum variance portfolio, what solver is, it's a linear optimizer. So what it will seek to do is it will seek to achieve some objective by changing other cells. In this particular case, for my minimum variance portfolio, the objective I want to achieve is I want my risk, or my standard deviation, which again is just the square root of variance, I want that to be minimized. And I want that minimization process to take place by changing the weightings across these 7 stocks. So what this is going to do is going to change those different weightings until it comes up with a combination of weightings that will minimize that risk. But I need to include just a couple of constraints here. Okay, my constraint I need to include, first of all, I need cell A25 to equal to 1. Why is that? Because the sum of the weights has to equal to 1. And I don't need any other constraints. So by default, when I opened solver here, it had a few other constraints. I'm just going to leave those out. I don't need them. However, if you were told that that you've got a short sale constraint, so that is, let's say that you're operating in a market or in a particular environment where you're not permitted to short sell stocks, then in that case you would need to add an additional constraint. You would need to add a constraint that all these weightings must be greater than or equal to 0. Okay, so that's what we would call a short sale constraint, that the weights must all be positive, because obviously a negative weight implies short selling a stock. In this case, I'm not going to impose a short sale constraint. I'm just going to keep my basic formula, and I'm going to select solve. Okay, it's found a solution. So what you can see is what Solver has done is actually changed these weightings, and it's come up with a combination of the weightings such that this standard deviation is now minimized. It's my minimum variance portfolio. So what I'm going to do is I'm going to record this information. So this particular portfolio, I'm going to take the weightings, I'm going to copy them by pressing Control C, and I'm going to paste them down here by clicking Control V. Okay. Then my mean return, my standard deviation, and my slope, I'm going to copy those as well. I'm going to right click here. Now because these are formulas, I can't just paste them, I need to paste special values. So if I right click and just click on this button here, that will paste them as numbers rather than formulas. You can see the numbers are still the same as what I've got here, but it doesn't have the underlying formula. And basically all I've done is just saved that. This is just like a workpad where I've just saved the parameters for that particular minimum variance portfolio. It's my starting point. Next thing I'm going to do, I'm now going to use Solver again, but now I want to calculate my optimal risky portfolio. So as I said earlier, my optimal risky portfolio is the portfolio where the Sharpe ratio, or the slope, is maximized. So in this case, my objective is that the slope value is maximized. Everything else remains the same. I'm still seeking to achieve that objective by changing my weights, and I still want this constraint that the sum of the weights has to equal 1. So I solve that value, click OK. We can see we've got a fundamentally different set of weightings as before, because this is basically the security selection decision that can construct that optimal risky portfolio with the maximum expected Sharpe ratio. So I'm going to copy those weights in, paste them, as I did before, copy the mean, standard deviation, and Sharpe ratio, paste special values, and I've identified those two key points of the efficient frontier. Now next part is a little bit tricky, but basically what we need to do is, it's not good enough just to have 2 points on the efficient frontier. I need to now identify what the shape of that frontier looks like. So to work out the shape, what I'm actually going to do is I'm going to plot in some points. We know that the efficient frontier is going to start at mean of 7.8% and a standard deviation of 18.5%, and it's going to move up and go through mean of 9.3%, standard deviation of 23.5%. So if I was to look on the graph up here, okay, what I know is that it's going to start at a point. So mean of 7.8 about here, standard deviation of 18. It's going to start about here, and it's kind of going to go in this shape. Well, what I know is that it's going to cover all these expected return values from 7.8 onwards. So what I'm actually going to do is I'm going to plot in some mean expected return values that I know that this efficient frontier is going to go through. And the way I'm going to do that is just, we know it's going to go through all the expected return values between these two numbers. So I'm just going to roughly identify points that are approximately halfway between. Now there's no science to what I've done here. All I've done is pick numbers that are approximately equal spread between these two numbers. And then equally up here, I'll choose some numbers that are again approximately equal spread past those values. It doesn't matter what numbers you put in here, you just want them fairly well spread apart. All we're doing is putting these parameters in so that we can then use them to identify the point on the efficient frontier that goes through these expected return values to enable us to identify the shape of that curve. So what we're going to do now is, we know that every point along the efficient frontier is the point whereby for a given expected return value, the risk is minimized, or alternatively, the Sharpe ratio is maximized. So the way that I can calculate this is going back into Solver and saying, Solver, I still want you to show for me the portfolios where the Sharpe ratio is maximized. I still want that achieved by changing the weightings, and I still want this constraint that the sum of weightings has to equal 1. But now I'm going to add an additional constraint, because I want the portfolio on the efficient frontier which calculates such that the mean return is equal to 8%. Okay, so I'm constraining it, just getting that particular point on the efficient frontier with a mean expected return of 8%. I'm going to go and solve that value. So solve has found a solution for me. As expected, that solution does have a mean return of 8%. And here are the weightings. So I can copy those in, paste them down, copy, paste special values once again for these values. And I've identified that particular point on the efficient frontier. Okay. If I now do this quickly and do it for the rest of these different points, okay, so I'm not changing anything in terms of my objective, still trying to maximize the Sharpe ratio by changing the weightings. All I'm going to change now is this constraint. It's because I want to move along. Now I want the point on the efficient frontier with an expected return of 8.3%. Solve that one. And I've got that particular combination of assets. Okay, keep moving along. So all I'm continually doing now is just changing my constraint and solving. Okay, in the interest of time, I'll move through this part fairly quickly, but just keep pasting those values in. Okay, now I want the value with an expected return of 9%. Okay, paste the portfolio weightings, paste the mean, standard deviation, and slope. Okay, and now I want those values past the optimal risky portfolio, because the efficient frontier will continue past the optimal risky portfolio. So I want those expected return values. Okay, paste those in here. Once again, next one now for what is the point on the efficient frontier that has an expected return of 10%. We can see now we're starting to get negatives, which means we're, in order to get this particular expected return value, we do have to short sell one of the stocks. Obviously, if you had imposed a short sale constraint, these weightings would be slightly different, and that would be a 0. But in this case, I haven't imposed a short sale constraint. And my last point here is just expected return value of 10.5%. Copy those in, paste, copy, paste special values, and I've populated the table. Now what you can see down here is at the time I was populating, because this graph is actually generated such that it's plotting the curve associated with the mean and standard deviation. At the same time as I populated that, it actually created the efficient frontier for me, and what you can see that the efficient frontier follows this nice smooth shape that we expect in theory. It's that same shape as what we see, starting at the minimum variance portfolio. The point where this capital allocation line hits the efficient frontier as a tangent would actually be my optimal risky portfolio, just along here. And in the green line there, this is my capital allocation line, starting at the risk-free rate, passing through that optimal risky portfolio and moving onwards from there. In the next video, we'll discuss in greater detail about how to generate these graphs, but that is creating an efficient frontier in Excel.